Hello everyone, I'm Simon and welcome to my third video. Now, this video I supposed it is a final part of my first video, which contains the content of Taylor's theorem. Things like how does Taylor's theorem take this formula, why this is true, and some practical applications of this kind of theorem. And the first part of my today's video is to end the topic of this part. And on the other hand, I would also love to talk about something related to sequence convergent, the definition of sequence convergent, and a theorem related to it. So basically, that is my plan for this video. And let's begin. So, let us recall what the formula of Euler to the x takes its form. It's something like that. Well, just one thing I should stress at this point, that is this little o notation. Basically, what it means that on this formula, start from the 1, 2, 3, 4, fifth term up to the infinity, the sum of these terms. It is, if you divided it with x to the cube, the limit of this formula is exactly equal to 0. So let me write it down. If you take the limit of x tends to 0, since from the first term, you see in the first term there is an x in the expression, and the second term there is a x squared, and so on and so forth. Since x tends to 0, then every term in this expression tends to 0 as well. So basically, this is what it tells you of this little o notation. And as I have written down here, we can introduce complex number into this expression and find out what is e to the ix, Euler to the ix, and Euler to the minus I times x. And we define I, a complex number, such that I squared is equal to minus 1. This is its definition. I mean, in the first place, it is being invented by the mathematicians to solve some equations that cannot be solved in the range of real numbers. And this is how it has been invented. And then follow this definition, we can formalize our expression of e to the ix and e to the minus I times x. It has been listed out here in 4. There's a recurrence relationship between I, every 4 terms of I, namely I squared, I to the cube, I to the fourth power. This forms a loop, and only elsewhere, i's nth power is just takes this 4 value, and it is a recurrence relationship. Now, if we conduct some manipulation on e to the ix and e to the minus I times x, we can get some useful information. Namely, we can find out how they are related to trigonometry functions sine x and cosine x. You see down here. And from these two expressions, we can derive a vital important formula. I guess even throughout the whole mathematical history, it is quite important, namely the Euler's formula, which names after Euler, a Swiss mathematician. Euler. E to the ix, what is it equal to? It is equal to cosine x plus I times sine x. And as I said, it has been proved, I bet, many times in a vital important role in the development of mathematics. Euler's formula. And from this formula, we can easily derive another formula that is equally, no, sorry, not exactly equally, but it is indeed also very important. Namely, de Morov, I don't know if I have pronounced this France mathematician's name correctly, but anyway, what it says is cosine theta plus I sine theta to the nth power is equal to cosine n theta plus I times sine n theta. And it can be derived very easily if you apply Euler's formula, since the content in this bracket is nothing else than e to the I theta. E to the I theta to the n is equal to e to the I times n theta, where it turns out to be the formula we would like it to be. And we have proved this formula. It is indeed correct. There are many usages when we think about this formula, this one. And I would like to talk about two of its applications. One is that you can find all the values of n throughout the integers. What is a value of cosine, let's say 2 theta, or cosine 3 theta, or any other thing, and so on and so forth. So how do you find that? Let's take cosine 2 theta, for example. Cosine 2 theta, so you know that n takes 2, and you just expand this formula explicitly. You see, it is just cosine theta square plus something. Well, that something is unrelated to what we are going to find because it is the real part of the expression, and the middle term contains imaginary part. So that's not what we are going to find out. And the final term is I to the square, so that is minus 1 times sine theta square. So the left hand side of this formula is equal to cosine theta square minus sine theta square, which we know that it is indeed equal to cosine 2 theta. And the same goes for cosine 3 theta and 4 theta and so on and so forth for these positive integers. You just open this bracket and written out the left hand side of a formula explicitly, and it's all done. Another usage is we can solve some equations related to or involved complex numbers. I've listed a example here. So this is the function, or no, the equation we would like to solve, the original equation, where z is a complex number. So before we actually solve that, I would like to stress one point a little bit, that the definition of a complex number, as you can see, it is it has two parts, a real part and an imaginary part, where we substitute x with r cosine theta and y with r sine theta. If it's not quite clear, I mean, if you can have a normal coordinate system where this is y-axis, this is x-axis, and you just draw a triangle, right angle triangle, and if this is r and this is theta, then the vertical distance to the x-axis is precisely equal to r sine theta, and well, the horizontal distance is r cosine theta, and that should be clear. And since we have the Euler's formula, we can simplify into this kind of form. Z is equal to r times e to the I theta. So that's the definition to a general complex number form. And then we come back to our solving the equations. We follow the procedure in this way. We times 2z, and the first term becomes 16 times z. The second term becomes 32 times z squared, and you can see that. And then by this kind of procedure, we can simplify to what we find it is easier for us to solve, and use the formula of Euler's equation to solve. Well, at this point, z cube is equal to 1 over 8. That implies the modulus, or the norm of this complex number, is equal to 1/2. Well, that comes to light because if you take z equal to r times e to the I theta, the component which controls how long it will be is just this radius rather than the angle. So there is a direct implication of the relationship at this point, this row. And after this point, and you just substitute, because you know that the radius is 1 over 2, 1/2, and then you just substitute the norm radius times e to the I theta, all squared, to the cube is equal to 1 over 8. And then you just apply the existing formulas, and then you find the corresponding angles. For example, you know cosine to the 0 is equal to 1, where sine to the 0 is 0. That's how we find these angles. And you can then work out what this z can take this value. Since this equation, it stresses z to the cube, third power. This implies that there are precisely three distinct solutions to this equation, and here it is. And the final point regarding to this example is that because we have to do some alternating changes to the original equation, so there is one solution to the new equation. It is not the solution to the original equation we would like to solve. And in this case, it is 1/2. It is not a solution to the original equation. This should be pay great attention to. Okay, that is all for the end part towards the first video, the Taylor series and its applications. This is all I would like to say, at least in one dimension. I may release new videos to explain more Taylor series on higher dimensions, but that is in other videos, not in this one. Now, let me come to the second part on sequence convergent. I have already give you the definition of this one actually on my first video, but let me recall what it is. It says, for all epsilon greater than 0, there exists such an n0, such that for all n greater or equal to n0, the absolute value of Sn minus L is less than epsilon. If the above condition has been satisfied, we say that Sn converge to L. This is the definition of sequence converge. Yeah, well, there's another starting point on how to understand this definition. That is, if the above condition has been satisfied, there are infinitely many Sn lies in the interval, open interval, L minus epsilon and L plus epsilon. There are infinitely Sn lies in this interval. That is another saying to this same definition. And then there is one final theorem I would like to say in this video. That is, every convergent sequence has only one limit point. And I should outline the proof of this theorem. We conduct this proof by contradiction. So the first step, we just suppose there are two distinct limits, L1 and L2. They are not equal to each other. This means that there exists an n0 for all n greater or equal to n0, Sn minus L1, the modulus of this result is less than epsilon for all epsilon greater than 0. This is precisely the definition. And then we can do something clever. We can choose this epsilon because it is a fixed value, and it is arbitrary, and we just take a value of epsilon that is helpful to us to complete this provement. And in this case, I take epsilon to be 1/3 the distance between L1 minus L2 to be the epsilon. So similarly, we can see that there exists such a n naught prime for all n greater or equal to n naught prime. Sm minus L2, the modulus of this result, is less than epsilon. This is also a direct implication from the definition. And then what about we take the maximum of this n0 and n0 prime, and then both these two conditions are being satisfied. And then there's a final and the most important step, that is how can we construct something that is contradict to the original assumption. You can see that by triangular inequality, we obtain something that is quite ridiculous, and then we realize that some mistake must be made by us, and it turns out that the mistake is L1 is not equal to L2. It is a mistake, and the truth is there should be only one limit towards a convergent sequence. This is how we complete the proof. Okay, that is all for this video. I shall stop here, and thank you for watching on this video, and see you on next video. Goodbye.